Okay, all good? All right. So so we're going to try YouTube today. So hopefully this will work, and hopefully we can keep doing that for the rest of the term. And now I see there's a lot of you. So I was worried that I would have sort of less feedback about who's there. I guess the downside is that you can't talk back to me, but I see lots of comments, so I know there's lots of you out there. So I mean, as with Learn, stop me if there's questions. Use the chat to ask questions, and I'll read the question and I'll try to answer it. Okay, and if there's any problems with, I guess if you can't connect at all, then that's bad. But lots of you can connect. So if there's any problems with the audio or the video, let me know in the chat, and I'll try to fix it. Okay, and so hopefully this will work. So let's get back to parsing. So, I mean, last time we looked at bottom-up parsing and top-down parsing, kind of contrasting the two. And I said we would look at LL parsing, or top-down parsing first. Even because it's simpler than LR parsing, and because some of the concepts that we're going to need are going to we can learn those concepts in the context of LL parsing first, and then apply them in LR parsing. So I'll step aside a bit. So this is what I had on the whiteboard last time. So just as a recap, so the idea of top-down parsing is that we're going to start with the start symbol of the grammar. And in this case, I'm using alpha as the current step in the derivation. And we're trying to build this derivation going from the start symbol of the grammar S all the way to X, which is the input string that we're parsing. Okay, so we'll start with alpha being S, and then each iteration of this loop is going to be one of the derivation steps. And the hope is that eventually we will get to alpha being X. And then within the loop, sort of the main thing we do is we find a production rule A goes to beta in the grammar. And and then we apply that production rule in alpha, right? So we take an A and that we find inside alpha, and we replace that A with beta. So that's what a derivation step means. And then, we did this little example. So I have a grammar here that defines the language A and A plus A. So these very simple expressions, these two possible expressions. And then I was parsing A plus A. And so we started with E, the start symbol of the grammar, and then we applied a production rule to get A, E prime, and then we applied another production rule to get A plus A. All right, so now, so hopefully that's okay. And now, there's a bit of magic in here, so I want to, clear up the magic, right? And so the magic is, how do I pick this production rule to apply at each step? And we had, we had a choice here when you have A, E prime. Well, in the grammar, there's two production rules that expand E prime. So you could apply one or the other of them. But, because the input is A plus A, the only correct one in this case for this input is this one, right? So then the question is, how do we choose a production rule based on the input that we are seeing? And there's going to be two pieces of information that we use. So I'm going to add here. All right, and now if my writing is too small, let me know. But I'm going to let A be the first non-terminal. In alpha. Okay, so and I mean we looked at that before in terms of the order in which we expand different non-terminals. But for the LL parser, because we're looking at the input from left to right, we're going to take the leftmost non-terminal and always expand that. And you might have noticed I used A here and A here. And really that non-terminal that we're trying to expand, already rules out a lot of options in the grammar. So, here I've got the derivation step A, E prime, and I'm trying to expand E prime. Well, obviously, I'm not going to use the first rule in my grammar, which expands E and not E prime, right? So the A is going to be sort of the first way that we narrow things down, narrow down which production rule to use. But then here, I still have this choice between these two rules. And so that's where I'm going to use a bit of the input. Okay. And so I'm going to add here, in brackets. So alpha, I'm going to say that alpha is some y followed by a big A followed by gamma. All right. And, if you think back to the conventions, so y represents a sequence of terminals in my grammar. And so that, so that ensures that A is the first non-terminal in alpha, right? Because everything before it is terminals. So now to decide which production rule to use, I want to look at a specific place in the input X. And the place that I want to look at is, after Y. And so, let me kind of write this over here. X, it has to equal YAZ. So the point is X has to start with Y. Okay, and why does X have to start with Y? Well, because if X doesn't start with Y, then I'm never going to be able to derive X from alpha, because Y is all terminal symbols, and terminal symbols never change to anything else, right? It's only non-terminal symbols that get transformed by the production rules in the grammar. Okay, so if my input doesn't, if my alpha and my input don't match up on some prefix Y, then I've already I'm already gone. I'm already lost. I'm never going to be able to parse this. And so really, I need to structure my algorithm so that it maintains this invariant that a prefix of alpha is a prefix of input. And in fact, the prefix that's all terminals has to match what's in the input. All right. So assuming I make the right choices to maintain this invariant, now I can I'm going to erase this line here and say let little a essentially be the little a in here. So let a be the first terminal in X after Y. All right, and that, so then in brackets, X has to be some prefix of alpha, and then some more terminals, and the first of them we're going to call A, and then the rest of them we're going to call Z. Right, A is one terminal symbol, and Y and Z are some sequence of terminal symbols. All right, and so now I'm going to assume I have a magic function, well, or really any function that you could possibly implement that is going to tell me what rule to use, right? What production rule to use. So let A goes to beta be the result of a function that I'm going to call predict, and the parameters to that function are going to be big A and little a. Okay, and so the key is going to be figuring out how do I actually implement this predict function, and I'm going to delay that for a little bit. But the point is, if it's possible, so if there is a function such that using big A and little a in every possible situation that this parser can get into, if you from big A and little a, if you can always pick the correct production rule to use, then the grammar is LL1, and you can parse it with this parser. Okay, so I write out a definition of an LL1 grammar in a little bit, but that's the idea. So if it's possible to decide what the right rule is at each step using only the big A and the little a, then the grammar is LL1. And the 1 in LL1 comes from the fact that we use the one upcoming terminal symbol from the input to make this decision. If hypothetically, if you had an LL2 parser or LLK for any K, then here the A would actually be a string of more than one terminal symbol, and you would have more information as input to this predict function. All right, so so let's kind of go back to the example. So in the example, well, my big A was E prime, so I know I'm going to pick one of these two rules. And then what's little a? Well, my alpha is AE prime, so Y is A, and my input is A plus A. So what comes in the input after the Y? Well, it's the plus, right? And so using the fact that I want to expand an E prime into something that starts with plus, I have to pick the right rule. And of course, I picked this one because that expands to something that starts with plus. But if there was ever a situation where picking this one was also the right thing to do, or a possible right thing to try, then this grammar would not be LL1, and I wouldn't be able to parse this. Okay, so any questions? Stop me if there's questions, or post in the chat if there's questions. All right. Okay, so our language has two possible inputs, right? A plus A, well, or two actual words in the language. So A plus A and A. So what happens? What if the input wasn't A plus A, but what if the input was A, right? The other possible input. So then I would have A E prime, and what would the algorithm do? So it would say, let it big A be the first non-terminal. So big A would be E prime. And now, what's Y? Well, Y is A, right? Y is the piece of alpha that comes before the first non-terminal. And so then what's little a? So little a is the first terminal in the input, okay? But, my input is now, just A. So the A in the algorithm is the first symbol in the input after the A, okay? But there is no symbol after the A, right? The string ends, the input ends after the A. Okay, so in fact, this algorithm isn't really well defined for this input. Basically, there is no first terminal in X after Y. Okay, if that's confusing, ask in the chat. But okay, so we're going to fix the algorithm so that it can deal with this special case. And once again, the problem is when the input ends, right? That's the special case that we're dealing with. So what I'm going to do is make sure that the input never ends. Okay, and so the way I'm going to do that is I'm going to add a special terminal symbol that is going to be a terminal symbol that marks the end of the input. Okay, and so this is something called augmenting the grammar. So augment a grammar. All right, and I'll kind of underline it in blue, but and what this means is I'm going to add a terminal dollars, and sort of the traditional symbol to use for this is a $sign. So I'm going to add a terminal symbol and add a production rule, and I'm going to say S. Well, I here, in general, I'm going to say S prime goes to S $sign. So here, S is the old start symbol, and S prime becomes the new start symbol. Okay, so I mean, it's maybe easier to see on the example grammar that we have here. So what I need to do is add a new rule, and just to confuse things, so the old start symbol was E. So I'm going to say, well, maybe I'll call it S prime. S prime goes to E $sign. Okay. So what have I done? So my start symbol used to be E, and so but now it's S prime, and so this new grammar accepts all of the same strings that the old grammar did, except for each such string there has to be a $sign appended to it. Okay, and so if I have my language definition here, right? So the set of strings that this grammar generates or specifies is now a $sign and a. Oh, I got the wrong color. Okay, whatever. A plus a $sign. Okay, so basically I've changed the grammar so that every string now has this extra $sign appended to it. And, and then similarly, I'm going to change the algorithm. I'm going to try to parse an input that's actually X $sign. And then the $sign propagates here as well. So X $sign is going to be YAZ. Okay. All right, and then one more place in the grammar in the algorithm where I want to add the $sign. So I want to add the $sign here. Okay, so these are just tweaks that will ensure that here the A is never empty, right? Because the Y is going to be a prefix of X, and so even if Y is all of X, A can still be that $sign. So now if I run this algorithm instead, so I'm going to start with the start symbol followed by $sign, which is E followed by $sign. So my alpha starts as E $sign, and let's see. Okay, and so my input, let's say it's just A, but the algorithm is going to treat it as if it was a $sign. So at this step, I'm going to say let A be the first non-terminal in alpha. Or I suppose I should first do the first step, right? So at the very beginning, my big A is this big E, and my little a, well, it's the first terminal in the input after a prefix, but here there is no prefix, right? Because E is a non-terminal. It's the first non-terminal in alpha, and it's right at the beginning of alpha. So there are no terminals before E in alpha. So it's the empty prefix. So for that first step, the little a is also little a. And, I'm trying to find a way to expand a big E to something that starts with little a. So I use this rule, and I turn alpha into this AE prime $. And now in the step that was causing trouble before, I have Y is A, and X is also A, but now let A be the first terminal in X. So I guess this should be in X $, after Y. So now the A in the algorithm is actually $, right? So in the case, in the A plus A case, the A was plus. In the A, in the case where the input is just A, then there the A in the algorithm is $. And so I can call predict with E prime and $. And basically, predict needs to tell me if I need to turn an E prime, into a $, into the end of the string, which production rule should I use? And because I'm trying to find the end of the string, I should use this second one that turns the E prime into epsilon. And so then, if I turn the E prime into nothing, then I'll have just a $. And, this loop, it's trying to find a derivation of a $, and it's found it. So I succeed, and I'm happy with the parse. Okay, and I know so there were some questions, and right. So I guess the suggestion was to kind of use epsilon. So essentially, the $, takes the place of epsilon. Epsilon is tricky because epsilon is not a symbol. Epsilon is a representation of the empty string, so a sequence of 0 symbols. But essentially, this $, we're adding a new terminal that represents the end of the string. That represents that we don't want any more. Sorry, I'll stand over here so you can read that. So we don't want any more symbols to be added to the derivation. Okay, so now we've augmented the grammar, and we can parse both of these strings in this simple little language. All right, what else do we do? Okay, well, so we're going to have to implement this predict function, right? But there's one more sort of transformation that I want to do here before I go further, or before we look at how exactly we'd want to implement this predict function. And I'm just trying to see. Okay, whiteboard space. So I'm gonna do it here so that I can write code over here. Okay, so one thing that's still a little bit underspecified in the algorithm is this alpha, right? So you have this sequence alpha, right? It's a sequence of terminal and non-terminal symbols, and in here you're always looking for the first non-terminal in it, and then you're searching through the input to find the first terminal there, after a certain prefix. And we want this algorithm to run in linear time, right? The part of the point is we want a fast parsing algorithm that runs in linear time. And, there's already one loop here, so we can't really afford to have a second, a linear time loop nested within there. So essentially, we need a data structure that is going to efficiently represent alpha. Okay, and because we are, making changes to alpha at in a particular spot in alpha, right? There's this sort of spot where the first non-terminal is, and maybe after that non-terminal goes away, well, then maybe we advance to the next non-terminal. But we want a data structure that's efficient and that lets you kind of make changes in one place. Okay, and so the data structure that we're going to use is a stack. So, use a stack. And we're using a stack to represent alpha. So, but a stack isn't exactly what we want. So I'm going to say, I'm going to have alpha, and I'm going to divide alpha into some parts. And in general, I'm going to divide alpha into y, w, a, and gamma. So, again, going back to the conventions, y and w are all terminal symbols, and so a is the first non-terminal symbol, right? So, this is the one that we're going to be changing. Y and w, they're already terminals; they're never going to change. And then, gamma can be anything. It can be terminal symbols or non-terminal symbols. It's a sequence of symbols. And I like to, also draw sort of the parse tree diagram. So this is the parse tree that we're in the process of building. And if I can, and I'll draw a line here. So if you remember back to Wednesday's lecture, I talked about top down. So we're building the tree going this way, and at the same time, we're going through the input this way. And so, anything above the red line, we've already built. Anything below the red line, we are still going to build. And so I'm going to write y here. So y is the part of the input that we've already processed. And then, okay, w, a, gamma. So the stack, okay, so I need to write, oh dear, I can't write diagonally here. Let's see, w, a, gamma is going to be sort of this boundary of the parse tree that we haven't built yet. And then I'm going to say WAZ is the rest of the input string. Okay, so all right, so in general, the idea is there's the part of the input y that we've processed and we're done with, and in general on my stack might start with a terminal symbol. So that happens when I do this replacement. The way I'm going to implement this replacement is I'm going to want to pop a from the top of the stack and replace it with beta. And beta is the right-hand side of a production rule. So in general, beta starts with beta could start with a terminal symbol. So in general, I could have terminal symbols on my stack. So that's what the W represents. But then the input had better start with, the input after Y had better also match the W that the production rule told me it's going to match. Because again, if it doesn't, then there's no hope of parsing that particular input. So sort of my hope is, I'm going to match the W. Let me go back again. So there's kind of two operations that I'm going to be doing. I'm going to be popping a symbol off the stack, and if I, so let's see. So operations. So one operation is I pop a terminal off the stack. So and I'm going to say pop terminals W. Right? I mean, I'm going to pop one symbol at a time, but I'm going to pop terminal symbols off the stack as long as there are terminal symbols at the top, and I'm going to check that the input matches. Okay, so I'm going to take my stack. I'm going to pop things off as long as they're terminals. Well, they had better be the same terminals in the input because terminals don't change to anything else. Okay, and then the other thing that might happen is I pop a non-terminal off the top of the stack. So pop a non-terminal A. Okay, and so that's, if I've popped all the W off, right, I've popped all the terminals, and now the thing at the top of the stack is a non-terminal, well, then, then I need to do this stuff, right? I need to use the predict function to pick a rule and do the replacement following that production rule. So, then expand A goes to beta. All right, so okay, so the whole thing is basically, doing this algorithm, but incorporating a data structure where this piece of alpha is a stack, and I should kind of draw it on here. So this WA gamma in general is a stack with the top, I'll say T here, and the bottom here. Okay, and so the idea is on a stack, you can, push and pop things at the top, so you can make changes here between the Y and the W, and the general changes that you make are, one, you get rid of the W, so you pop off the W and you make it be part of Y, the input that you've processed already, and then once there is no W, once you have so W, it's a string of 0 or more symbols. So once it's 0 symbols, then there's an A at the top of the stack. And then you pop off the A and you do the body of this loop, right? Where you use the A in the predict function to give you a production rule, and you apply the production rule. And the production rule says replace A with beta. So that means I'm going to pop A and push beta in its place. Okay, so now I'm going to, write out what this algorithm looks like when we incorporate the stack into it. But if there's questions at this point, ask them now. Okay, I mean, you can ask questions whenever, but this is a good time. So I'm going to erase this augmenting because, so I have room for the algorithm. Okay, so basically I'm translating this algorithm with that stack data structure. So so this is going to be my final LL1 parser. Oops. So LL1 parser. Okay, and so, I start off with initializing alpha to be $. And so since alpha is the input that I've seen so far, and then the first non-terminal symbol, well, that input is empty, and so $$ is what I push on the stack. So I'm going to push $$ onto the stack, and so this is the equivalent of assigning or initializing alpha to $$ Questions? No questions? Okay. So, all right, so I push that onto the stack, and then, all right, this while loop, I'm actually going to turn it into a for loop, and I'm going to loop over the input. So A is going to be looping over the input with that $, added to it. So with that augmentation. And now, so, over here I said, there's two possibilities. Either the stack has a terminal on top or it has a non-terminal on top. So I'm actually going to deal with the non-terminal case first, because the terminal case is going to, advance me to, so if the stack has a terminal, then I need to match that terminal up with the input, and that's going to mean advancing in the input, so advancing in this for loop. Okay, so we'll do the second case first, and I'm going to actually make this a while loop rather than an if statement. So I'm going to say while top of stack is a non-terminal A, right? And I can say A in N, so it's a non-terminal, but that's just the convention of capital A represents a non-terminal. Okay, so if the top of my stack has a non-terminal, then what am I supposed to do? Well, I'm gonna pop A off the stack. I'm gonna find the right production rule. A goes to beta in predict of big A, little a. And then I'm going to push beta onto the stack, right, instead of A. So this is the part where, the algorithm said replace A with beta in alpha. Well, since alpha is represented by the stack, I'm popping A and pushing beta in its place. Okay, and so, why is this a while loop? Well, it's a while loop because beta might start with a terminal symbol, or it might start with a non-terminal symbol. If beta starts with a non-terminal symbol, then after I push it onto the stack, the top of the stack is still a non-terminal symbol. So I want to keep doing this, right? I want to, I might make multiple replacements here until I have the top of the stack being a terminal symbol. Once the top of the stack is a terminal symbol, then there's nothing I can replace it with anymore. So that's when I will go to this, second operation of popping W. I essentially want to get rid of all the terminal symbols that are on the stack to find the next non-terminal this A that's going to expand to something again. But when I pop them, I'm going to check that the input matches them. Okay, so outside of this while loop here, I'm going to pop, and I'll call this B. Okay, so I'm popping something off the stack, and it has to be a terminal symbol, because if it was a non-terminal, I would be stuck in this while loop. And I'm going to check. So if B is not equal to A, then I'm going to give an error. And this is basically, the grammar was saying, the grammar was saying that the next thing in the input should be B, but it was actually A, and so it's not the string is not in the language of the grammar, right? So in this example, for example, if I had the input AA, and the grammar was saying, well, you should expand the E prime to a plus A. Well, then the plus and the A wouldn't match, and so I would get an error there. So actually, the thing that can also happen is here the predict function might give an error. So the predict function might already at that point say, well, there is no way to expand an E prime into something that starts with A, right? If my input was AA, I'd need to be expanding E prime into something that starts with A. And, this rule doesn't do it, and this rule doesn't do it. So an error can actually happen also here, where I call predict. So predict. So I'll say or error. Okay. I suppose the place where I would get an error down here is if the input was, let's say, A++. All right. So then I would be here. I would see A, and then my next input symbol would be plus. And so the predict function would say, well, to turn E prime into something that starts with plus, turn E prime into plus A. So now my next symbol in the input would be A, and sorry, my B that's on the stack would be A, and my A that comes from the input would be plus, because the input would be A++, and so these wouldn't match, and so I would get an error here. All right, so either of these places can cause the algorithm to give up and say, well, this is never going to reach a derivation. If I manage to go through the entire input, then then I'm done and everything parsed okay, and I'm going to accept. So if I manage to get here, I'm going to accept. And sort of, why is that safe? Well, it's safe because I started with my stack having a $sign on the bottom, and my stack it's always going to keep that $sign on the bottom because none of the original rules in my grammar ever changed the $sign. Right? I can never. I'm only ever changing non-terminals on the stack, but the $sign is a terminal. So I have that $sign there, and here the $sign, it's a new terminal symbol, so it can't appear anywhere inside X. It can't appear anywhere inside the grammar. And so if I reach the end of this loop, that means I must have found a derivation from this thing that ends with the $sign to this thing that ends with the $sign, and it must have been a derivation of X. Okay, so and we've got good question. So the question is, when we push beta, are we pushing the terminals and the non-terminals in reverse order? So I mean, it depends on which order you consider forward or reduce or reverse. But the idea is that you want to replace A with beta and in alpha. So, and your alpha, has the top of the stack here. So the sort of the leftmost symbols in beta, you want to end up at the top of the stack. So if you view the stack as having the top on the left, you would need to push the rightmost part of beta first. So I guess you could call that reverse. Yes. So if beta is plus A, I would push the A first and then the plus, so that the plus ends up at the top of the stack. So yes, it's a form of a reverse order. Yes. Okay. And in the original order, well, I mean, it's depends what you mean by original order, right? You want, if the top of the stack is on the left, you want the left part of beta to end up at the left, so at the top. And so if you're pushing one symbol at a time, you do need to push the leftmost symbol last and the rightmost symbol first. Okay, yes, so that's a good point. Okay, so now I have the algorithm written in terms of the stack. And so there's no more alpha explicitly. It's sort of implicit in the stack. I don't have to do these linear scans within alpha. I'm just pushing and popping. Okay. So I'm just pushing and popping on the stack to simulate the replacements of A with beta in alpha. Okay. So now I have the algorithm. And I can move on to, how do I implement this predict function? The predict function, that's still the mystery in both of these algorithms. Okay, so how would I implement predict? And where did I hide my eraser? That's my other mystery. Oh, it's here. Okay. All right, so what do I erase? So I'm going to erase this part, and if we need more space, I'll erase more later. Okay, so how do we implement predict? Well, so predict of big A, right? Okay, so how are we going to implement predict? Well, it turns out I want to use this stack-based version of the algorithm, and I want to implement predict so that it tells me to do everything that's not completely stupid. Okay, so predict is going to tell me, all the possible production rules that could kind of sort of make sense in a given situation. And, to formalize, kind of sort of make sense, I want to use rules that are not sort of obviously going to hit an error right away. And I guess I'm specifically thinking about this error down here. So here where I'm making a prediction, I want to avoid production rules that would lead to an error immediately down here. Okay, so I'm going to define the predict of A and little a as a set, and it's going to be a set that, well, it's got to have rules of the form A goes to beta that are in the set of production rules in my grammar, such that, and now it comes. So they have to be rules from the grammar. That's kind of obvious. And but now, which rules, right? And so, which rules should I pick? Well, here, let's say my input was A plus A. And so my next input symbol, my little a in the algorithm was plus. And I was trying to expand E prime to something. Well, I probably want something that starts with a plus, right? So I'm going to be pushing one of these right-hand sides onto the stack. And then, after the loop down here, I'm going to pop the first symbol in that right-hand side off the stack. And I'm going to compare it to what I saw in the input, this little a. But in my example, that little a is a plus. So, I should really use this production rule because it gives me something that starts with a plus. Okay. So, when is it not completely stupid, or when does it make some sense to turn big A into beta? Well, maybe if beta starts with little a, right? That's a good time. But I'm actually going to expand that a little bit, because what could also happen is I push beta onto the stack, but what if beta starts with a non-terminal? Well, then this while loop is going to continue executing. All right. So really, the condition for pushing beta onto the stack is to say that beta should derive something that starts with A. So I'm going to say there exists a gamma such that beta derives a gamma. Okay, so it's a good idea to replace A with beta if it's possible, starting from beta, to derive something that starts with A. All right, so the common case is when beta itself actually does start with A, right? In that case, I guess beta equals A gamma. There is some other gamma that you can put after A that equals beta. But in more generally, that beta could go and have more derivation steps applied to it before this while loop needs to end, and before you need to check that what you have at the top of the stack, so sort of the result of beta, actually starts with A. All right, so so that's going to be a condition for predict, and the sort of there's a shorthand or a word for this. It's often called a first set. So let's see, how did I want to do this? I'm going to say A is in the first set of beta, and where I need to define the first set of beta is really just this definition. So it's the set of all A's such that there exists a gamma such that beta derives a gamma. Okay, so I haven't really changed anything. All I've done is, given this expression a name. It's called sort of first of beta, or A being in the first of beta is equivalent to, there exists a gamma such that beta derives something that starts with A. Okay, and we could be almost done defining predict here, but there is one other sort of more subtle case, right? And again, to recap, we want it to be the case that when we exit this loop, that the top of the stack has A on it. Because if it doesn't, we know that we're going to hit an error immediately after exiting this loop. Okay, so how else could the stack end up with something? End up with A on top immediately after pushing beta? Well, we have an example in our grammar here. We have this other production rule that where beta is the empty string. Okay, so what could also happen is if beta is the empty string, then after I push beta on, I pop A, I push beta. What's going to be at the top of the stack? Well, it'll be whatever was on top of the stack, sort of below the big A, before I started running this loop. Okay, so that's a special case. When beta is empty, well, then what ends up on the top of the stack is not going to be something derived from beta, because beta is empty, but it's whatever was on the stack before. All right, so I'm going to say or, and do a big open bracket. So or what? Or, well, beta is the empty string, or I'm actually going to say beta derives the empty string, right? Because beta itself might not be empty. So beta might have some non-terminal symbols in it. So I push those on the stack, but then I keep running the while loop, and let's say those non-terminal symbols, all eventually end up into the empty string. And so by the time I get out of the while loop, essentially beta has turned into the empty string. Okay, so beta goes to the empty string, and what? So I mean, I want to somehow say that's what's on the stack after beta is this little a. All right, and so I'm gonna screw. Where are we here? So what do I want to say? Well, the way I'm going to say it is that S prime. So the augmented start symbol of the grammar can derive some sentential form that has a followed by little a in it, and I'm gonna just put a gamma and a delta before that, and those can be any sequence of symbols. So all I'm saying is there exists some sentential form that has a little a in it, and if that's the case, then it's possible that the stack had a little a delta on top of the stack, and I pop off a, replace it with beta, beta turns to nothing, and then the stack has little a. All right, so I'm going to say there exists gamma and delta such that the start symbol derives something that has a little a with a gamma before it and a delta after. Okay, and then I'm going to give these things names. So if beta derives the empty string, so I'm going to call that nullable. So I'm going to say that beta is nullable if and only if beta derives the empty string. And then I'm going to define what's called a follow set. So I'm going to say the follow set of a non-terminal A is the set of all terminals that can appear after it in a sentential form. So all the little a's such that there exists delta and gamma and delta, whatever, so that S prime derives gamma, big A, little a, delta. Okay, so if I compute the first sets, I should underline them. So if I compute the first sets, the nullable sets, and the follow sets, for the right sequences of symbols, I'll be able to define predict out of them, using these sets. Okay, so this is sort of the order in which we build these up. We're going to define these sets, and then out of those we define predict. So I want to kind of do it by example. So I'm going to do it for this particular example grammar. And I mean, as we do the example, I'll try to tell you the general ways that you would compute these. In the Appel textbook, and possibly other textbooks as well, but specifically the textbook by Appel has a nice clean algorithm that computes all these sets for all the right sequences of strings, all in one loop and efficiently. And that's also the implementation that I'm giving you in this J Lawler tool on the course website. So I need to remind myself to remind you that is on the course website. So on the course website, there's a thing called J Lawler, and it's a Java implementation of the various algorithms that we're going to look at in the lectures. And so specifically, it has a calculation of the first set, the nullable sets, follow, and predict for the LL parser. And then it also calculates the related things for the LR parser. So that is a tool that's there for you to use for your project to generate these sets. Now it's written in Java, but I mean, you can use it from other languages because you feed it a grammar and it computes everything for you, and you can then put its output into a file and read it from whatever language you're using. But I'm giving you that code for kind of two purposes. One is so that you have that code, you can use it for your project. But number two is so that you have an example of a full implementation of all of this stuff that I'm doing in theory in the lectures. So if you kind of want to look at more detail of how this stuff actually looks in code, that's a place where you can look. So you're welcome to use that. If you want to, as an exercise, re-implement it for so that it's not in Java but in Rust or C++ or whatever language you're using. I mean, I think it's a good exercise, but I think it's a bit too much work to require you to do that. But at least it's there for you to look at the code and sort of clarify any ambiguities that you have in your understanding of the code. Okay, so right. So how are we going to compute these? All right, so I'm going to compute nullable first, and we're going to need to know nullable for all the right-hand sides of production rules. All right, so for this grammar, I need to know nullable of of E $. So let's see, let's do that. Right, nullable of AE prime, nullable of plus A, and nullable of the empty string. All right, well, so nullable of the empty string, that's easy. It's true, right? The empty string does derive the empty string because it already is the empty string. So that one is easy. And then, the other ones are also easy because they all contain at least one terminal symbol, right? Plus A, and $. So nullable of plus A. Let me just write them all together. Plus A, E prime, and E $. Is false. Okay, because in these strings, well, the non-terminals, the E prime and the E, they might expand to stuff, but no matter what they expand to, you're gonna still have those terminals in there. So the overall string will never expand to the empty string. Okay, so these are all false. The place where it could get a little tricky is if you had a right-hand side that consisted entirely of non-terminal symbols. And at that point, you have to look in the grammar to see how those non-terminal symbols are expanded, whether they can in turn expand to something that is the empty string, right? Or itself expands to the empty string. So in general, you would need like a work list-based algorithm of you start with all the right-hand sides that are the empty string, and then here I would say, well, since the empty string is nullable, then E prime, the symbol E prime can be nullable because it can expand to the empty string. And then any production rules that had only E prime on their right-hand side, their left-hand side symbol could also be nullable. So you'd have a work list-based algorithm to compute all the right-hand sides that can turn into the empty string. Okay, so that's nullable for this example. And then how do I compute the first sets? Well, again, you're going to need first sets for the right-hand sides. All right, and so the first set of the empty string, well, how is that defined? Well, it's defined as all the terminal symbols A such that the empty string derives something that starts with A, and the empty string can't derive anything that has terminal symbols in it because the empty string doesn't derive anything other than itself. So the first of the empty string is the empty set. There are no terminal symbols that anything it derives can start with. And then the first set of E prime, and more generally, the first set of anything that starts with a terminal symbol is just going to be that terminal symbol, right? Because again, so AE prime, no matter what E prime changes to, what AE prime changes to is always going to start with A, because that A is never going to end, never going to change. All right. Questions? No. Okay. All right. And then what else is there? So first of plus A is going to be plus. All right. And then finally, first of E $. Okay. And so, so this is going to be more interesting. So what you need to do for first of E $, is look at what E could expand to. Okay. And so for that, I'd need to look through my grammar at all the rules that expand E. In this case, there's only one, and it's a rule that expands E to AE prime. And then I would look at the first set of AE prime. So if there were more rules expanding E, I would look at the first sets of all of their right-hand sides. All right, so in this case, the first set of AE prime is A. And so the only thing that E can expand to, E always expands to things that start with A. The other thing I would need to take into account here is if E was nullable, then E could expand to the empty string, and then I would need to look at the symbol that comes after it. So then I might need the $sign there. Okay, but E is not nullable again because the production rule expanding E goes to AE prime, and AE prime is not nullable either. Okay, so I have to compute nullable and first, and then to compute follow, it's kind of the more challenging one. And no questions. All right. So how do I compute follow? Well, it seems I need to look at all possible sentential forms and see if they have a little a in them. So actually, what we're going to do is we're going to look at the production rules. And how could I ever get big A, little a, one after the other in a sentential form? Well, I'm going to say if I have a production rule, B goes to alpha A gamma. Okay, so what am I saying? And this is in R, so in the set of rules in the grammar. So in the grammar, I have some production rule that has A in its right-hand side. Right? So, okay, so what can happen? Well, if I apply this production rule to some sentential form, it's going to change some B to, alpha A gamma. And then the gamma might derive something. And what I'm looking for is a sentential form where A is followed by little a. And so that could happen if the gamma derives something that starts with little a. Okay. And, how do we know whether gamma derives something that starts with little a? Well, we ask the first sets. So we're going to do the first computation for gamma. So, any production rule that has a non-terminal on the right-hand side, we look at what comes after, and we take the first set of it. And then we're going to create a constraint that says the first set of gamma needs to be a subset of the follow set of A. Okay, so this is saying anything that gamma derives, whatever terminal symbols that starts with, are possible symbols in the follow set of A. All right. Now, if I see A followed by gamma, what else could happen with gamma? Well, gamma itself could be nullable as well, right? So in addition, I'm going to say if gamma is nullable, okay, so if gamma is nullable, what happens? So the A gamma could turn into just A, right? The gamma could turn into nothing. And so then, what would come after the A in the sentential form? Well, the B turned into alpha A. So whatever is after A, or whatever was after the gamma, could have come after the B, right? Before I applied this production rule, whatever was after the B is now after the A, after the gamma has turned into nothing. So then if gamma is nullable, then I have to take the follow set of B and add that to the follow set of A. Right? So anything that can follow B can also follow A. So I just take whatever set I have for B and I add it to A. So the way that you use these constraints is that you initialize all the follow sets of all of your non-terminal symbols to the empty set. And then you process these first constraints to kind of initialize all the sets. You take these first sets and you add them to all of the follow sets. And then you kind of do a fixed point computation. You repeatedly process these constraints, taking a follow set of B and adding it to the follow set of A. And you keep propagating the sets until things stop changing. All right. So, let's try to do that for my example grammar here. So let's see. I guess over here. All right, and that eraser is here. Okay, so I see E on the right-hand side of a production rule. I have this right-hand side E $, and so that is going to give me the constraint that $, has to be in the follow set of E. And then similarly, I have E prime here, but so for E prime here, gamma is empty, and the first of the empty string is the empty set. So I wouldn't get any constraint out of this one, but in the nullable case, so this is a case where gamma is nullable. And so this says the follow set of B is a subset of the follow set of A. So in this case, B is E and A is E prime. So I would say that the follow set of of E is a subset of the follow set of E prime. Okay, and so now I can, propagate the set. So for the follow set of S, of S prime here, I just have the empty string. I have no constraints that would tell me that S prime could ever be followed by anything. And it can't. I mean, S prime only ever happens as the start symbol, and it immediately goes away, and then it never comes back. But now for the follow set of E, well, I would initialize it to the empty set, but then I have a constraint that says $sign has to be in it. And then for the follow set of E prime, I would also initialize it to the empty set, but I have a constraint that says anything that's in the follow set of E has to also be in the follow set of E prime. Okay, and that's because, we have a sentential form E $sign that has a $sign after an E, but that leads to a sentential form E prime $sign that has a $sign after E prime. Okay, and so now we can use these to compute the predict table, using this this formula. So the predict table, it's a table that has all of the non-terminals along one axis, so along the columns, let's say, and all of the terminal symbols, so A plus and $sign, along the other axis. Okay, and so you need to follow this formula. So when big A is S, then I guess it's S prime. Sorry. So big A is S. So essentially in this column, you either have this rule or you don't. Okay, because it's the only rule that expands S prime. And do we have it if the symbol is A? Well, we ask, is A in the first set of S prime? Where are we? No, is A in the first set of the right-hand side of this rule? So the first set of E $sign is where? First set of E $sign is A. So basically, we would have that rule only in the case of A. All right. Now, same thing for E. We would ask, what are the symbols in the first set of AE prime? So it's AE prime. The first set is A. So for A, here we would expand, have that rule that says E goes to AE prime. And in the other rows, we have nothing. So the idea is, if I ever get into a situation where I'm calling predict on, say, big E and plus, well, that's going to give an error. My predict function is going to not return any rule because none of the rules could ever lead to a successful parse, right? They're all going to error out immediately. Okay, and then finally, I've got E prime. And this is where I have a choice of two rules. So, I'm going to look at the first sets of the right-hand sides of those rules. So the first set of plus A is plus. So in the plus case, I'm going to say, E prime goes to plus A. And the first set of epsilon is the empty set. So that rule, I shouldn't use anywhere. But that rule is where I use the second part of the predict definition, where I go to look at nullable right-hand sides, which epsilon is. And in that case, I want to look at the follow set. So, I want to look at the follow set of E prime. The follow set of E prime has a $sign in it. So for the case where little a is a $, I'm going to have this production rule. Okay, so now I have this predict table, and I can use this table to implement the predict function, right? I have my non-terminal big A and my terminal little a, and I just look it up in the table. Now, the key thing is that this table, each entry in the table is not just a single rule, but a set of rules, right? There's a curly brace here, so it's a set of rules. But in this particular case, each set is either of size 0 or 1. Okay, and that's good because that means using this table, I always know exactly which rule to pick. Okay, and so now I know I'm sort of out of time, but I've got one last important definition to wrap up LL parsing. So I'm going to say that a grammar is LL1 if, so I'm defining LL1 here, if the size of predict A and little a is less than or equal to 1, for all non-terminals big A and terminals little a. Okay, so all right, so this definition, so we say that the grammar is LL1 if this predict table always has 0 or 1 entry in each cell. And in that case, the table always tells us, oh, use this rule, use this rule, use this rule, right? It can tell us unambiguously what the only possible, non-stupid thing is to do at any given time. And then the algorithm that I erased is going to repeatedly do the only non-stupid thing, and and it'll either succeed or fail. Like it'll either parse the input to completion, in which case, yes, the input is in the language of the grammar, or it will fail somewhere along the way, which means the input didn't match what the grammar was saying. But the point is the algorithm doesn't need to do any backtracking or make any decisions, because at each point this is predetermined. And grammars that are not LL1, where sometimes there is more than one possible choice that makes sense, they can't be parsed by this algorithm because it would have to backtrack. So we looked at left associativity not being LL1, and that would lead to a case where you have 2 or more rules to try in some situation. And yes, thank you for the questions or the corrections. That should be E goes to $, not E goes to epsilon. E prime goes to epsilon, not to $. Okay, so now we have LL1 parsing done, and I'm eager to get to LR parsing because that's what I'm recommending that you implement in the project. But we're done with LL, and now we can move on to LR in Wednesday's lecture. So any last questions about LL or LL1? Okay. All right, so hopefully the YouTube thing worked out. So I'm gonna end the stream here, and I'll post the recording online. If there's comments about how well YouTube is working, you can talk about that on Piazza. So have a good couple of days, and hopefully we'll be back on YouTube on Wednesday. Okay, bye.